All right, looks like we're started and all ready to go. We'll wait about 1 minute to get started. Just wanted to make sure everything was ready to go on our end. And we'll start at 1 p.m. Eastern Daylight Time, which is in about a minute. Oh, you have the same problem that I was. Like it's not
plugins.
Yeah.
Maybe fix it.
Are you on Firefox or whatever you're on? I actually did do that first. Just 1 second, we're getting Aurora set up here. We'll be right with you. I did actually do this, and I did this, and then I went in here, and then maybe not. Yeah. I just clicked a bunch of these screens. Yeah. And then I think I like went in and out or something again. Like I did that. And then perfect. Oh my, here you go. Okay. Focus on the one. You're like on. Like you're actually like a video, like people can see you. Got it. All right, I think we're ready to go after those technical difficulties. I think Aurora's all set up and we're good to go. So please, if you're watching us live, type in your questions on the Google Hangout. You can also do it on the discussion page, and we'll be monitoring both of those and asking your questions as we go. I see a few of you have joined us. So welcome to Alien Worlds Office Hours number 3. All right, let's begin.
So the first question from the Office Hour 3 discussion is from H. Holy, and it says, this paper, and the reference is at the bottom if you would like to look at that, apparently identifies hot, very low density worlds. In particular, Kepler-79d has a mass of 6 times Earth, a radius of 7.16 times Earth, a density of 0.09 grams per centimeter cubed. Temperature is an unknown, but they indicate 634 Kelvin and a suggested helium/hydrogen atmosphere. Escape velocity looks about 10 kilometers per second, and molecular velocities, hydrogen-2 is 2.8, helium is 2.0. This would seem to suggest that its atmosphere cannot be retained over a long period. What is your opinion of their long-term atmospheric retention and how this world will evolve?
Yeah, so this is a great question about when we have some of these hot Jupiters or hot Saturns or very big planets that are at least much larger than the Earth, and actually probably start much more massive than the Earth as well. And they likely probably cannot form in the right next to their star. They likely have to form, beyond the frost line, beyond about 3 astronomical units, but they actually migrate down close to their star. We think that's what happens. There's a couple of different mechanisms by which a planet can actually be formed in the outer part of the solar system and actually migrate in. And it can actually migrate all the way in to form those hot Jupiters that we saw in the radial velocity module, this last module that people have been working on. Oh wait, they're about to work on the one that's going to launch tomorrow. So you don't maybe know about these yet. You will after tomorrow. Sorry. There are a series of really large exoplanets, Jupiter-sized, but some smaller, like the one that this student just asked about, that actually are right next to their star. And as we'll see, those actually are worlds that are not very common, but are actually the easiest to observe. And so when we were first identifying exoplanets, now 20 years ago, those were the first kind of exoplanets that were discovered because they're the easiest to find. They actually produce the largest amount of signal. But the question really was about the atmosphere on these worlds. And so it does turn out that if you get a world like this too close to its star, it can actually heat up the outer part of the atmosphere, and that actually can then get those molecules to actually move at escape velocity and actually move off the surface of the star, or sorry, of the planet. There are other things that happen too. Some of these stars actually have winds, like our sun's wind, and that can actually blow off material. And we actually have evidence of exoplanets orbiting very close to their stars, where we actually can see that there is gas being thrown right off those planets. So we can actually see the planet, but then we can actually see there's basically kind of a trail of gas as it's being either blown off by the stellar winds or just escaping via the escape velocity that we've talked about in this class so far. So that can happen a lot. It does, of course, mean that over time, these worlds will lose mass. That matter is just, those molecules are being blown off. And so it's especially the lightest elements, the hydrogen, over time can be totally blown off, at least the outer parts of the star as you get, or the planet. As you get probably closer and closer to the inside, you're going to get denser gas. It's going to be more gravity, and so the escape velocity is going to get much higher. But certainly the outer parts can be blown off over time, and so these planets can really go on major diet by actually migrating in. In our own solar system, we actually, the way that we think our planets actually formed actually was through a giant migration. Jupiter and Saturn, we think, migrated very far into the inner solar system. They didn't go all the way to the sun, but they actually came into probably a couple to a few astronomical units. Remember, Jupiter is at 5 astronomical units, and it came into maybe as close as a couple astronomical units. That's actually one of the reasons we think Mars is so small, is because Jupiter actually came all the way in and then actually migrated back out. So planet migration, we think, is a very common process, even in our own solar system.
So the next question is actually related, so we should do it in order.
Okay.
So it says, in question 6, the graph shows Saturn is cool enough to hold on to H2. But if it was orbiting close to the sun, it looks like its temperature would be high enough to let the H2 escape. Are there identified exoplanets that might fit this hot Saturn type, either having their atmosphere depleted of lighter elements or in the process of doing so?
Yep. So we certainly know of exoplanets that are probably in both those categories. Certainly massive, giant gas worlds, like a Jupiter or a Saturn, that are have moved close enough to their star where now the velocity of the molecules is fast enough to overcome the very large escape velocities of those worlds. And so we know of worlds where that certainly is happening. And like I said before, we actually have even seen evidence of some of that gas being ripped off the star, or jumping off the star if it's just the escape velocity. And so we can actually not only see these planets transiting still, and we can see their radial velocity signature, which you're going to learn about starting tomorrow. But we also see evidence of the gas that's coming off this planet, the hot gas that's being come off this planet. So yeah, we certainly see that, and there's some evidence of a class of planets where basically hydrogen has already been stripped off because they've been there for so long. And so what you're left with is kind of the denser gas. There's probably hydrogen still at the center again, because again, the centers of these planets, the densities and gravities are high enough that the escape velocities are very, very hard to overcome.
So now I'm going to switch to a question that's coming from the Google question
excellent.
answer. It says, why do the planets all orbit in the same plane? And why do planets' moons seem to orbit in the same plane as that of the solar system?
Ooh, well, that's a great question. Why do planets all orbit in the same plane? We'll talk a little bit about this, and I think we talk about planet and star formation in a couple modules from now. We'll also talk a little bit about this whole migration thing a tiny bit. But really, it's because planets, I have to get a prop here. Because planets form, here's a Frisbee, that's all, it was on my wall. Planets really form in a disk like this. They form from a disk of gas. Basically, as the gas of a star is collapsing, gravity is pulling it all together. And if there's a little bit of rotation, which there's going to be because it's not going to be perfectly symmetric in the collapse, as it gets collapsed down smaller and smaller, it's going to start rotating faster. Imagine an ice skater that many of you may have seen. When he or she pulls her arms in at the end, spins faster. The same thing happens with a gas cloud in space. As you shrink it down, as it gets smaller and smaller, you're conserving angular momentum, which means you actually begin rotating faster. As you rotate faster, it actually spreads the material out into a disk. And so it's from these disks, which we can observe. We can actually go and look around other stars now, and we can actually see disks. And it's from these disks that planets then form. And because they're all rotating in the same direction and are formed from a pretty thin layer, all the planets, although they move a little bit around in this way, are all in basically the same alignment. Now the other question was about moons. Well, it turns out the moons aren't necessarily in the same exact orientation as the solar system, but they often are found in a plane. So if you look at the moons of Jupiter, they're all basically in kind of a similar plane, or the moons of Saturn are in a similar plane. And that's because we think that all of the moons around, say, Jupiter formed in a disk around the planet Jupiter. It was kind of a mini solar system. In fact, the exact same physics that takes place in Jupiter, and actually some really cool things happen. I'll just share with you one that we won't probably talk about for a little bit longer, but there's one really neat trend we think that happens in solar system formation, that denser material we find closer to the sun. And that's because of the way things collapse, that it's much easier for you to collapse, turn something like rock or something like metal, like an iron, to turn that from a gas phase, which everything starts as, into a liquid or a solid that you can actually build a world with. You can do that at really hot temperatures. Whereas if you want to form a world with something like water, you have to actually be pretty cold to turn that into ice, right? It's water vapor when it's very close to the sun. And so you actually end up building worlds in a solar system that are made of, iron or rock and iron very close to their star. And then you can actually start building worlds with rock, iron, ice, all sorts of different ices as you get farther away, and you can build bigger worlds. Where Jupiter is so far away that it should basically, all of its terrestrial worlds that you can stand on should actually be ice. But it turns out, because there was a mini solar system, a little mini system around Jupiter, and Jupiter, while it was itself collapsing, was producing enough heat, it actually created this little sequence within its system. And actually the moon Io, which is one of the closest, at least larger moon, it's actually almost all rock. Even though it should be ice, for where it is in the solar system, but because Jupiter was actually giving off so much heat, it only allowed a world to form made of mostly rock. So neat little cool tidbit about solar system formation. And we'll actually talk about that more in a future module.
Now we're going to go back to the discussion. And the next post is, much talk has been made of terraforming Mars in the distant future. Given that evidence suggests that Mars has already lost much of its thicker past atmosphere for a variety of reasons, not least of which is the current lack of significant magnetosphere, what hope do you see for creating a Martian atmosphere suitable for human habitation without life support suits? Can we replace Martian atmosphere faster than it is lost and eventually achieve a new equilibrium suitable for humans? Or is future Mars colonization likely to be limited in domed environments?
Wow, what a question. Well, I for one, never am someone who says anything is impossible. And I certainly think Mars terraforming is likely possible. Probably not in any of our lifetimes. Certainly not in any of our lifetimes. But who knows what technology will be, 100 years from now, 200 years from now, 500 years from now, 1,000 years from now. The concept is actually pretty simple. Mars has, just about the right gravity to just barely hold on to water. So basically, water kind of gets held on in vapor form, but can escape a little bit. Oxygen's similar. It's, it escapes kind of very, very slowly from Mars. So after, like billions of years, it's all gone, but it actually leaks out just very slowly. It does hurt that maybe Mars doesn't have a strong magnetic field at this point that actually can allow high energy particles from the sun to come in and do some molecular disruption of things like water as well as other atmospheres. But if you could imagine, we had the technology to pump things like oxygen and or nitrogen or other things into the atmosphere, which we certainly could. I mean, you could imagine developing giant greenhouses or giant oxygen machines that were taking, I don't know, either rocks from the surface, which are very oxygen rich, or maybe we find subsurface water, I don't know, or we use the mostly CO2 that's on the polar caps, who knows? But maybe there's a way that we can turn some of that into atmosphere, and we can do that faster than the loss rate. Certainly, I don't think that's impossible, but it's probably going to take a very long time. I imagine that, if there's any kind of Mars habitation in the next century or maybe even two, it's going to be kind of under domes or in Mars spacesuits. Certainly, the first few missions will be like that. But that's a really cool question. But I wouldn't rule it out. Humans are also extremely ingenious at coming up with very clever ways of doing all sorts of things. So I imagine some point in the distant future, Mars has a chance of being habitable.
All right, we're going to go back to the Google Hangout questions now. Could you go into a little detail about how we might develop the technology to get a spectral reading on the atmosphere of super-Earths or Earth-sized rocky planets? How much of a step will James Webb or TESS provide, or TESS some other coming telescopes provide?
Oh, that's a really great question. I guess I didn't go into as much detail in the MOOC about that, but I would. So the basic way that you actually go into the, I mean, we have some of that technology now, I guess is the first answer. So we actually don't need to develop a whole lot of technology at this point to be able to take one of those spectral readings. Part of it is just being able to do what we can do now better. And in fact, we have measurements of atmospheres of super-Earths right now. They're not actually overly interesting right now. I'll tell you a little bit more about that in a second, but we do have some measurements. But the basic idea, of course, is that you have a transiting planet, and it's orbiting a star, and you take a spectrum of the transiting planet when it's passing in front of the star, and then the light passes through the star's atmosphere, and it also passes then through the planet's atmosphere if it exists. And then you can actually wait to be safe, wait till the planet is not transiting, and you can take another spectrum, and that gives you what the star is. And if you can do that really, really well, if you can take the measurement of star plus planet and just star, now you just literally subtract the two, and you're left with planet. And so we've actually done that. We've done that using Hubble Space Telescope. We've done that from the ground at some facilities. The technology is not, to do the actual spectroscopic part is not actually very hard. The hard part is that, if you've got a tiny planet with a tiny little bit of an atmosphere around a really big star, that's a tiny, tiny signal. And so you need to take very, very, very precise measurements. So things like the Hubble Space Telescope is pretty good at that. What will be even better is the James Webb Space Telescope, which the student who asked this question mentioned, because it's going to be an even bigger telescope than the Hubble Space Telescope. And because it's bigger, it's going to collect more light. And it's also going to look in the infrared, where the contrast between the planet and the star is a little bit better. But mostly it's just that this telescope is so big and the instruments are really new, and so we can take very, very precise measurements of this spectrum, of the planet plus the star, and then a really, really precise and accurate spectrum of just the star, and we can subtract the two, and we can get the atmosphere of both super Earths, which we've already done, as well as get down to Earth-sized planets. We think we should be able to do that around some of the closest stars. TESS, which is the other instrument, this is Transiting Extrasolar Survey Satellite Survey. I cannot remember which way it goes, and I'm on the team. But Transiting Exoplanet Survey Satellite, I think, is what that is. And it's not going to be able to do this test, but what it's going to be able to do is just identify the nearest planets. So it's not going to be able to do any type of spectroscopic work to find atmospheres, but what it will do is identify these small rocky worlds around the very closest stars, and then we'll turn James Webb on some of those targets, and we'll be able to look to see if those worlds indeed have atmospheres and look at the content of them. Like I said, we've been able to do this already with some super Earths, certainly with many Jupiter-sized planets, Neptune-sized planets, but actually a couple super Earths. It has not been overly interesting. A lot of the small worlds that we've only been able to do it for a couple of the smaller worlds. They do look like they have atmospheres, first of all, so it's not like they don't have atmospheres, which already is kind of interesting. But they look like they kind of are very cloudy, maybe even steamy atmospheres that have no real features. And of course, that's not as interesting if we want to look for tracers of life or other products in the atmospheres. The atmospheres themselves are pretty, I don't know, boring may be too strong, but they're featureless. And so they don't tell us much more besides them just being there, which in itself is actually interesting. But we'd of course like to see more. We'd love to see things like oxygen and methane, or things that might tell us that there could be life. So, cool question.
All right, so another question from the Google Hangout is regarding accretion. Are all protodisks pure gas, or are there elements of solid material like dust or even pebbles and rocks part of the clouds eventually forming the protodisks?
Oh, wow. So this is regarding how planets form from the accretion of material from disks. And the question is about if are they pure gas or is there dust? There probably is some dust to start. Probably not small pebbles to start or rocks. Those get actually manufactured in the disk. They actually go from probably being a disk of mostly gas and then some dust. And over time, that dust forms smaller, grains, and those grains stick together and form pebbles, and those pebbles stick together and form rocks. Rocks stick together for boulders, and so on and so forth. And to be honest, we don't know exactly how that happens. A lot of the people who model these things actually just, they inject, rocks into their disks after some amount of time. And they say, look, oh, they formed some size. But we actually don't know exactly how that happens. But we do observe dust in the disk. So when we look out into the galaxy and see these disks around stars, we actually see this. We see the gas from them, which we can see mostly using radio telescopes. But we also can use things like infrared telescopes to actually see dust in these disks, which has actually been heated by the star, and so it kind of glows in the infrared part of the electromagnetic spectrum. So it's some dust and some gas, but early on, most of it is in a pretty gaseous form, but there is some dust. In fact, we think that part of how you actually form molecular gas that leads to the formation of stars and disks is actually on dust grains. And so you actually have to have some dust probably to even form these molecules, the base molecules in the first place. So it's some of both, but probably no rocks and pebbles until some of that dust has kind of stuck together. And that sticking together process is something we don't know necessarily a lot about.
All right, I'm going to jump back to the discussion forum. And a question from H. Holy. Saturn's moon Titan has an escape velocity equal to 2.6 kilometers per second. Applying the average velocity formula for nitrogen at 94 Kelvin, 10 times this velocity is 2.9 kilometers per second. This velocity is a little higher than the escape velocity. Does this imply that the N2 atmosphere is leaking away very slowly, and that it was thicker in the past or being replenished, or any other factors at play? Conversely, I think you should just answer that, and then I'll ask the second part.
That sounds good. I'll answer that one first. So, I mean, those two numbers are very close to each other. So if nitrogen is leaking out of the Titan atmosphere, it's probably happening very, very slowly, since those numbers are very close to each other. To be honest, I don't know enough about Titan chemistry, which is actually quite complicated. Titan does have a nitrogen-rich atmosphere, but it also has a huge number of hydrocarbons, things like methane, ethane, butane. It's basically gas, like gasoline or petrol-filled world. It also has weather. It's the only large moon in the solar system that actually has an atmosphere. It actually has weather. We have evidence from the Saturn Cassini mission, as well as the Huygens probe that actually landed on the surface of Titan. It's one of the worlds we've actually sent a probe and landed on. Two, there's evidence of weathering, things like clouds, of lakes, of probably rain. It's not water lakes or water rain. It's probably things made of hydrocarbons, things like methane lakes, methane rain, methane clouds. And when you have weathering, a lot of interesting chemistry happens. So, weathering on Earth, just having the rain, which is actually a little bit acidic, interact with rocks, that actually causes the rocks to actually get broken down a little bit. And in that process, you actually pull carbon dioxide out of the atmosphere. It's actually one of the ways that carbon dioxide is removed from our atmosphere is actually through just weathering from like raining on Earth. And so some weird chemistry happens, and I don't know enough about the chemical reactions in a nitrogen hydrocarbon atmosphere on the surface of Titan with weathering to know how that affects, say, the nitrogen content. It very well could be that you do some very weird things. If there is no weird chemistry happening, I imagine maybe there was a little bit more nitrogen in the atmosphere early on, but my guess is because those numbers are so close to each other, it's a very, very long time to deplete the nitrogen. But yeah, eventually, if indeed a little bit can leak out, then eventually it will eventually go away. But I imagine that's pretty hard to do.
So the second part of the question says, conversely, Mars has an escape velocity of 5 kilometers per second, and its hottest surface temperature is 310 Kelvin. This just about gets the needed velocity for N2 to escape slowly. CO2 should be easy to retain, yet today, Mars's atmosphere is very thin. This suggests other forces at play, e.g., lack of a magnetosphere to block the solar wind and flares from stripping the atmosphere, or perhaps lack of volcanic activity. Can you elaborate on the importance of other factors in the composition and density of atmospheres? Can we determine the atmosphere a priori of, is it the case that we have, or is it the case that we have to observe the atmosphere?
Well, I'll answer the last question first. The case is really we have to observe the atmosphere, because even as we see in our own solar system, different worlds are very different. I mean, Venus, which is only a little bit closer to the sun, is about the same mass and size as the Earth, has a totally different atmosphere than the Earth. It's much thicker than 90 times the atmospheric pressure on the surface, and it's almost all carbon dioxide. So it's a very different atmosphere. As the student said, the Mars's atmosphere is extremely thin, also almost all carbon dioxide. And so, and we just talked about Titan, which has a nitrogen rich, but full of hydrocarbons and methane rain and stuff. So all sorts of weird things are happening in just our own solar system. So, and we don't know how all those, what the myriad of possibilities are in other solar systems. So really, we probably have to measure an atmosphere to really say much about it. But the processes that form them and shape atmospheres are probably pretty similar. Some were mentioned by this student. I mean, things like volcanic activity is probably what supplies the major gas source for most terrestrial world atmospheres that are certainly don't have enough gravity to hold on to the initial hydrogen and helium. On Earth, a lot of our atmosphere comes from outgassing of volcanoes. So the nitrogen, the water, things like that, the carbon dioxide. So a lot of that can come from outgassing of volcanoes, something we think still is happening on the surface of Venus, probably not happening on Mars anymore, which is partly why the atmosphere is actually so thin, is it's not being supplied by things like outgassing. It can be also supplied on Earth, certainly, by things like life. Almost all of the oxygen that we have in our atmosphere that's important for us to breathe comes from life, comes from plant life, plankton, things like that, algae. So a lot of the plant life that we have on Earth is supplying the carbon dioxide. It can also be removed through lots of processes. I mean, I mentioned just briefly in the last question about weathering. That's a major way that carbon dioxide is removed from our atmosphere, and that can happen on any world where there's weathering, and you can have chemical reactions that actually pull gas out of the atmosphere. You can also have life is one on Earth. Of course, we are pulling oxygen out, but plant life is pulling carbon dioxide out of the atmosphere. It's another thing that reduces our carbon dioxide level. You can have things like solar wind or solar particles interacting with molecules. So the high energy particles from the sun, or actually even UV radiation from the sun, can actually break apart molecules. So you could have water molecule being split into its composite hydrogen and oxygen component. And if your gravity isn't then strong enough to hold on to those individual components, the molecule's gone. And that's probably a major reason or major way that Mars atmosphere has been lost. Probably both the water, certainly, because when you break water apart and you've got two hydrogens and an oxygen, the hydrogens just go away. And if you don't have enough gravity to hold on the oxygen, the same thing happens. But probably even the CO2, some of the CO2 on Mars has been broken apart by solar radiation and high energy particles from the sun. So that certainly has happened. There's actually a mission at Mars now, MAVEN, which some of the professors and researchers in our department here at Boston University are working on, some of whom you've heard from already. Michael Mandillo, who we saw in the interview segment in the Boston Public Library, is one of the scientists on board MAVEN, not on board, but who is helping with MAVEN. And this is a mission that that one of the main objectives is to actually understand what's happened to especially the water, but certainly the atmosphere on Mars. So this is a very active area of research, but there are lots of things that we know about that I just talked about that both can supply oxygen, supply atmosphere, or sources, or sinks, places that can remove atmosphere. So, cool.
There's also not a consensus on which is the most important.
That's right. Yeah, Aurora is exactly right. We don't necessarily know which is the most important in all of these either. Like I said, I mean, I don't, for something like Titan, I have no idea what the chemistry is. So I have no idea the role that weathering plays in that. So yeah, it's definitely an area of active research.
So back to the Google Hangout.
Yeah.
What is your opinion on focusing on a one-way mission to Mars instead of NASA's current plan?
Well, I think a one-way mission is pretty crazy. I mean, if we could do a round-trip mission, you could sign me up right now. I'd go, honestly. But one way, I think that's crazy talk. I think going to Mars would be spectacular. I mean, I think pushing the envelope of human exploration is important to us as a species. I think there are scientific reasons for going, having someone who is a geologist or a biologist or a paleontologist who could look at especially microbial fossils potentially, having them actually be able to be on the surface of the planet and investigate rocks kind of real time could have huge scientific impact. That said, sending people even one way, let alone round trip, which I think is the right thing to do, is extremely costly. I mean, it's very expensive to send humans into space and be, very, very safe because you need to protect them from radiation, you need to protect them from high energy particles, you need to make sure they have enough food for the journey, which to Mars, if you did kind of the very fastest you could go, you're still talking kind of 6 to 9 months on the trip. You have to make sure you have enough fuel to get there and back and down to the surface and back, and oxygen, and deal with waste, and it's very costly to send that. It's much cheaper to send a little robot or a little rover that can walk around the surface. And I'm not sure we're in a place right now economically where that makes a lot of sense. I mean, as you may have just heard, I think it's a spectacular thing that we should do as a species and as a civilization, is explore the solar system and maybe ultimately the galaxy. But I'm not sure we're in a place where that is financially a good decision. But I think a one-way mission's crazy. I mean, really. I'm glad people are gonna try to do it and gonna go, but I think it sounds pretty crazy to send people there just to die.
I don't want to go.
No, and I'm not signing up for that one. I'll sign up for the round trip, but I'm not signing up for the one way. That just seems crazy talk to me. But hey, it's, I guess, another piece of human exploration. But I also think there's things that we can spend our money on scientifically more efficiently. There's a lot more we can know about even other places in the solar system, let alone all the countless other worlds that we're learning that are much cheaper than that. And certainly, there are many things back here on Earth, making sure people, can eat and have a place to live and things like that are also things that are very important, and maybe more important than sending people to Mars. But I do think there's something about sending people to Mars that can inspire us to be a better civilization and a better planet and a better people, which may end things like hunger and homelessness. I also think some of the technologies that we have to develop if we're going to do that can actually help us in the end, can actually help us purify water and make sure that there are no more waterborne diseases in the world. So there actually are some really good things that something like going to Mars could do for society in general. And I think eventually we will.
All right, so back to the discussion. There's a question from Mitch that says, is it possible in theory to refuel the sun? From my understanding, the sun will vaporize anything that gets too close and blow it away. But if we could add more material like hydrogen to it, could we extend its life?
Wow, could we refuel the sun? I mean, in theory, if you could just get enough of it, you could probably just dump it on, and that would work. Because the sun would actually probably redistribute this a lot. When Aurora and I were looking at some of these just before we started, we were imagining a giant, syringe that you stick right down the center of the sun, and then you just, inject the hydrogen right into the center. But of course, the syringe might burn up and all that. If you could get enough hydrogen, you probably could prolong the sun's life. The problem is, where do you get that hydrogen? I mean, essentially, you need to get it from another star. And we certainly don't have the technology to do that right now. Remember that the sun is, 99.9, maybe even at least 99.9% of all the material in the solar system. And so, it's not like we can throw Jupiter in and it would do anything. That's a tiny, just bit of mass compared to the mass of the sun. So you really need to get it from probably another star or maybe a giant cloud of gas somewhere floating in space. So yeah, theoretically, if you dumped hydrogen onto the surface of the sun would re-equilibrate, and some of that hydrogen would sink to the core, and you would prolong the sun's life. But you'd have to get it there. And right now, I don't see an easy way of getting any more hydrogen onto the sun. So I think we're probably, for the time being, stuck with the sun running out of fuel in about 5 billion years. But it's 5 billion years, so we got some time. A lot of really bad things happened before then. So, like the Earth's oceans boil away and some other terrible things. So lots of other things happened before then. So yeah, leave on that positive note.
So back to the Google Hangout. Question from Louisa says, do you think we will find new types of stars, celestial bodies, as our technology evolves, or is it just going to be more of the same?
Oh, that's an awesome question, Louisa. So I think we'll find new things. Every time we make big technological advances, we always find something new. We find a lot of the same, but I think we find always new things. And one of the new things that's happening in astronomy now, and will be very big in the next several years, is looking in the time domain, we call it. So, taking giant maps of the entire sky, not just mapping where everything is, but now looking at it and maybe taking another map in a few days, and then taking a map another few days, and maybe doing that for a decade. And when you do that, you not only see how things move, because the stars actually move through the sky a little bit. You see how planets move and asteroids and things like that. You also see how they change in brightness. So some stars vary, some flare really quickly, some explode like supernova. But to be honest, we don't really have a good handle for what all of the things that could happen that likely do. And so in planning some of these new telescopes and observations, people are being very open to the idea that we are going to see things that go bump in the night, seeing things that flicker or explode or flash that we don't know what they are, because we've never looked, at least this deep, into the universe in the time space, at least as often. There is a telescope called the LSST, the Large Synoptic Survey Telescope. It's an 8-meter class telescope being built in Chile right now. That's going to basically take an entire image of the southern sky every 3 days. And we've just never had that level of data, and it's actually going to go very, very deep. And so we've just not had that quality of data, at least in kind of the time cadence, ever before. And so, yeah, we're very open to there being surprises, and there likely will be. We will likely find new objects and learn some new things about some of the ones we already knew.
So that's all the questions we have from the discussion and question A.
Okay, I should see if there's any on my, last time I got some on email. I'm gonna check that really quick.
All right.
They came in from YouTube, I think. Let's see. If you have any other questions, those of you who are still on, feel free to type them in. I think we've answered most in there. Nope, doesn't look like any new ones here. Well, while we're waiting to see if there's any additional questions, I hope some of you guys have been watching the new Pluto images coming in. We'll do some more, certainly in our update module. One of the things we'll talk about is Pluto, but probably we'll be sending little notes about it. Maybe our video email next week probably will be about Pluto. And the New Horizons mission, which is on its way to Pluto, and actually almost there, just over a week from now, it will be, it's closest to the dwarf planet Pluto. But there's already been some really cool images. If you just Google or search the internet for Pluto, you'll see some pretty spectacular images already. There was actually a glitch on the spacecraft this weekend. And it actually kind of shut down and lost communication with Earth briefly, and that would have been a terrible, terrible tragedy. But it looks like it's come out of its safe mode, and they're going to start normal operations again tomorrow. So I think all appears to be well with the spacecraft, and we'll be talking a little bit more about it later in the class. But you should stay tuned and keep up, because I think it's an exciting thing that's happening right now. First time we'll actually going to this very distant world, one that's not a planet anymore, but used to be.
So we have a new question.
Sweet.
Can you talk about brown dwarfs versus large planets like Jupiter?
Sure, that's something I know a lot about. Yeah, so for people who don't know, the term brown dwarfs is basically objects that are large balls of gas that aren't quite massive enough to start fusing hydrogen and being a star. So that limit happens at about just under about 8% of the mass of the sun. So once you get just below about 8% of the mass of the sun, no longer can you actually fuse hydrogen together to make the light that we see in the sky. Turns out you can fuse a type of hydrogen called deuterium. That actually sounds like a subtle, specific point, but it actually is important to this question. You can actually do that down to just about 1% or so, just over 1% of the mass of the sun. I think I have those numbers right. It's only 8% for, yeah, right? Yeah, I got those right. So we call those things brown dwarfs if they are less massive than about 8% of the mass of the sun. They're no longer a star, but they're really not a planet. They're big. In fact, we think most of them are probably formed in the same way that stars are, from the collapse of clouds, and that when stars are formed, you form some small ones and some big ones. As you'll see from the next video email, Aurora and I were just at a conference that was all about exactly that topic, like how many stars get formed at a different size or mass when stars get formed. The entire conference was about that. It's called the initial mass function. And that actually extends down into the brown dwarfs, where we think they form probably pretty close to the same way that stars form. Where it gets a little bit hazy is probably when you get down to a few, 1 to 2 or 3% of the mass of the sun. Most people would still call those brown dwarfs, but some of those may form in disks around stars. And so there are other people who might call those planets because of how they form. But the general rule is about 12 or 13 times the mass of Jupiter, which is about 1% or so of the mass of the sun. You no longer can actually fuse anything in these objects. So you can't fuse even this deuterium, heavy hydrogen. And so those we call planets. So once it's below about 12 or 13 solar masses, Jupiter masses, we actually call those planets. Of course, this is semantics, and there is actually a current debate over whether we should call a planet based on, or a brown dwarf based on their mass, or based on how they're formed. The latter of which is actually pretty hard to tell sometimes. Sometimes we just see an object floating around and we don't know, did that form like a star collapse from gas, or did it form in a disk and maybe got kicked out? So we don't actually know. So I would think most people do it based on mass. And if you're about 8% of the mass of the sun or more, you're a star. If you're kind of between 1 and 8% roughly, you're a brown dwarf. And if you're below 1%, you're about a planet. And Jupiter is about 0.1% of the sun. So it's actually quite a ways from being, you have to go about, like I said, 12 to 13 times more massive for it to actually become a brown dwarf. And even a lot more for it to become a star. So it's a big planet, but it's not that big.
So there's another question.
Yeah, awesome.
Have you gathered enough information about other solar systems to be able to say if our solar system is typical or in some way extreme?
Oh, is our solar system typical or extreme? We probably actually don't have enough information. In many ways, it actually looks pretty typical. We found now lots of systems that have a bunch of terrestrial worlds in the interior and some bigger worlds on the outside. There are also worlds. There are also systems where you've got some giant planets on the inside. It's really hard to find a perfect analog to our solar system, partly because if you remember from, module 2, you remember Kepler's laws, the farther you are away from the star, the slower the planet's orbit. And so if we're doing something like transit method, or even this new method that we're going to start learning about tomorrow, the radial velocity method, you have to wait for that planet to actually orbit, in sometimes multiple times, right? So Jupiter takes about 12 years to go around once. And so if we wanted to detect a Jupiter with Kepler, that would take 36 years, remember, because we want to watch it 3 times. Well, we haven't been looking for exoplanets that long, right? So we couldn't actually see a Jupiter using Kepler, right? Turns out we could detect a Jupiter using this method we're going to learn tomorrow, but it still takes 12 years to do one orbit. When you get to the other farther away planets, it takes even longer, right? So it's really hard to find an exact analog, and we're just now getting the technology to be able to find kind of Earth-sized worlds. But we're really not at the place where we can actually detect Earth-massed worlds at the distance of Earth. So our technology is not actually up to speed. We actually couldn't detect Mars right now. We couldn't detect Mercury. We found lots of worlds that have, or lots of systems that have terrestrial worlds in their interior, some that are very small, some that are Earth-size. Of course, most of them are around the smallest stars in the galaxy, which are the most common type of star, which is, that's probably what makes us different, if at all, is that we don't live around the most common type of star. We live around one that's actually, in the minority, certainly in the, maybe 20% of stars are stars like our sun, if that. So that's probably what makes us the least common. Did I answer everything?
I think so.
Okay.
There's a question that says, how excited are you for James Webb?
How excited am I for the James Webb Space Telescope? I'm a little bit excited. I'm not going to be super excited. I have a couple reasons. I mean, the James Webb Space Telescope is going to be amazing. It's going to be, Hubble 2.0. It's going to have amazing images. It's going to do incredible science. I guess my reluctance to be jumping up and down on my chair right now is you know, I'm going to wait for it to launch successfully and operate successfully. But the other thing is that it's cost a lot of money. And so it's actually taking a very large chunk of the astronomy research budget for NASA. And, you know, it will be a great resource for the community and everyone will have access to it. But, you know, there's only so many hours in the day and so many days in the year. Just like Hubble, it's going to be very competitive to obtain time on it, and for a very, very large cost to the community. Not everyone will get to use it. And so this is one of these things we have to balance as scientists, as politicians. You know, it's an amazing instrument. It's going to be state of the art. It's going to be able to do things like detect atmospheres of exoplanets, and I think that's a spectacular use for this telescope. And I think if we find evidence of life and stuff, then you'll see me jumping up and down on my chair. But I also sometimes worry that, like, again, we could spend some of that money on redistributing and having more people engaged in science, and that actually also might be a great thing. So I'm excited, but I'm not. I have some concerns. That's probably the most honest answer. But you know, in 10 years after it's launched, and maybe if we've detected oxygen and methane in the atmosphere of an exoplanet, come back and ask me again, and I'll probably tell you it was the greatest decision ever. Because I do think that would be the greatest discovery ever.
When is it launching?
Aurora asked when it's launching, if you didn't hear that. It's supposed to be the end of this decade, but these things usually get pushed back. So I bet, you know, early 2020s is when it really will launch. 2019 is nominal right now, but it will likely. The really cool thing would have Hubble still be alive and James Webb up at the same time. That would be a really cool thing to have them both happening. Hubble is there until it doesn't work anymore, and it's still working just fine. So we hope that Hubble lasts many more years. And I just heard that they're going to have funding for Hubble basically until it doesn't work anymore. So I think that's an amazing decision because it is already up there, it works, it does not cost a lot to maintain. And so I think it'd be really exciting if we had both James Webb and Hubble up at the same time.
That's all the questions we have now.
That's all the questions we have now. Well, it looks like we're just about out of time. Wow. Well, those were awesome, awesome questions. Unless there are any final ones, and I'll let Aurora do one final check through the questions. I'll check to see if there's any that showed up on my cell phone YouTube. Oh, is there? No, someone just subscribed. If there aren't any other questions, thank you for joining us, either for those of you who joined live or those who are going to watch on YouTube afterwards. We will see you at the next office hour, which I don't remember, but Aurora's going to look up really quickly. We'll certainly see you when we launch tomorrow.
Thursday the 16th.
Thursday the 16th. So Thursday the 16th.
A
little over a week away. We'll have our next office hour. So as you have more questions, Aurora will post a thread on the discussion forum. Keep asking questions. Join us live, and stay curious.